Hello everyone, this is Tarun from Data Science Department. My topic is Model Learning in Theory of Computation. About Model Learning in Theory of Computation. Introduction to Model Learning. Model learning involves the process of understanding and deriving models from data. It is crucial in the fields of machine learning and artificial intelligence. This presentation will explore the theoretical foundations of model learning. Introduction to machine learning. Machine learning to supervised learning, unsupervised learning. In supervised learning, there are two classifications. One is classification, and second one is regression. And in unsupervised learning, clustering, density estimation, dimensionality reduction. Definition of model learning. Model learning refers to building a mathematical representation of a system based on observed data. Models can be used for predictions, classifications, and understanding system behavior. The accuracy of a model is often assessed using various performance metrics. There is a pyramid diagram about the learning pyramid: lecture, reading, audio visual, demonstration, discussion group, practice by doing, teachers teaching others. Historical context. Model learning has roots in statistics and computer science. Early work in the field focused on regression and classification techniques. With the advent of computational power, model learning has evolved significantly. The historical context, we have different segments. Just go through with that segments in the given diagram. Types of models. Generally, we have different types of models in the model learning. Machine learning models like classification models, regression models, clustering, dimensional reduction, deep learning, and etc. There are various types of models including parametric and non-parametric models. Parametric models assume a specific form for the function being learned. Non-parametric models do not make such assumptions and can adapt based on data. This is the similar difference between the parametric and non-parametric models. నీకు చెప్తే అర్థం అవుతలేదారా? Supervised learning. Supervised learning. Supervised learning involves training a model on labeled data. The goal is to minimize the difference between predicted and actual outcomes. Common algorithms. The goal is to minimize the difference between predicted and actual outcomes. Common algorithms include decision trees, support vector machines, and neural networks. Supervised learning. Supervised learning is a branch of artificial intelligence, that is AI, focuses on training models to make predictions or decisions based on labeled training data. Labeled data. This is the label data and labels which are connected to the model training concepts and which is interconnected to the predictions, and then the objects will be displayed. And we have the database town and test data. These are the total equipments of supervised learning. Unsupervised learning. Unsupervised learning deals with enabled data to find hidden patterns. Clustering and dimensionality reduction are key techniques in this area. Examples include k-means clustering and principal component analysis, PCA. That PCA is known as principal component analysis. Unsupervised learning have data input, unlabeled data, hidden structure recognition, data recognition. These are the main concepts or main components in the unsupervised learning. Reinforcement learning. Reinforcement learning is a type of model learning based on agent environment interactions. Agents learn to make decisions by receiving rewards or penalties. This approach is widely used in robotics and game playing. Reinforcement learning in machine learning have input raw data, environment, output. This is the basic diagram of reinforcement. Just go through this. The role of algorithms. The role of algorithms. Algorithms are at the core of model learning, determining how data is processed. Different algorithms can lead to varying model performance. Choosing the right algorithm depends on the problem, domain, and data characteristics. Machine learning model, which have the problem statement to the data collection, to the data pre-processing. Select algorithm, training, evaluate, and output. There is an interconnection between the evaluate model and select algorithm. If accuracy is less, then only it is applicable. Computational complexity. The complexity of model learning algorithms can significantly impact their effectiveness. Understanding time and space complexity is essential for effective computation. Theoretical models help in analyzing the feasibility of learning tasks. There is a computational complexity theory graph that having consists of NP and NP hard. Intersection of these concepts having NP complete, which is in the ratio of easy to hardest. Learning theory. Learning theory studies the mathematical properties of model learning. It provides insights into convergence rates and generalization capabilities. Key concepts include probably approximately correct PAC learning. Theories of learning. In learning theories, we have different categories like internal and external. In internal, there are two variations, mental and physical. Coming to the point of external, personal and environmental. In mental, constructivism and physical, neuroscience. In personal, behaviorism, environmental, communities of practice. Bias variance trade-off. The bias variance trade-off is a fundamental concept in model learning. Bias refers to error due to overly simplistic assumptions in the learning model. Variances refers to error due to excessive sensitivity to fluctuations in the training set. It is a general graph diagram of bias variance trade-off. Overfitting and underfitting. Overfitting occurs when a model learns noise in the training data. Underfitting happens when a model is too simple to capture underlying patterns. This is the basic difference of this. Balancing between these two is crucial for effective model training. There is a general graph between loss and EPCOs. This topic which differentiate the underfitting and overfitting with validation and training. Model evaluation techniques. Evaluating model performance is essential for assessing its predictive power. Common metrics include accuracy, precision, recall, and F1 force. Cross-validation is a technique used to ensure the model's robustness. There is a general information about this. Just go through this one. Applications of model learning. Model learning has applications across various fields including finance and healthcare. It is used for anomaly detection, recommendation systems, and predictive analytics. The versatility of model learning makes it a valuable tool in many industries. Challenges in model learning. Challenges include dealing with noisy data and high dimension space. Model interpretability is critical, especially in sensitive areas like medicine. Ensuring fairness and avoiding bias in models is a growing concern. Future directions are the fields of model learning is evolving with advancements in deep learning and AI. Integration with other domains such as neuroscience is a promising area of research. Ethical considerations will play a pivotal role in the future of model learning. Conclusion: model learning is a dynamic and essential within the theory of computation. It combines theoretical insights with practical applications to solve real world problems. Understanding its foundations is crucial for advancing technology and science. Thank you. Thank you for your attention and participation in this presentation. Thank you very much.